De la Escuela de Ingeniería y Construcción del Tecnológico. Estamos muy contentos hoy en nuestro primer día de celebración de toda la semana. Y para culminar este día, tenemos la presencia y la colaboración de la doctora Sandra Houston, profesora emérita de la Universidad de Arizona State, quien fue profesora y también en algún momento directora de la Escuela de Ingeniería Sostenible y Ambiente Construido, que es el nombre que tiene la escuela ahí, como les decía, en la Universidad Estatal de Arizona. Ella se unió a esta escuela en 1984 y dentro de sus áreas de especialidad se incluyen la ingeniería geotécnica y la ingeniería geoambiental. Además, dentro de sus muchas áreas de investigación e enseñanza, los proyectos que ha desarrollado, que son muchísimos, ha sido, como les decía, aparte de directora de la escuela, ha sido directora del Comité de Modelado y Propiedades de Suelo del Geoinstituto de la Sociedad Americana de Ingenieros Civiles, que ustedes ya conocen, y ha sido una miembro activa en lo que es el sistema o el programa de mentores a mujeres en la ingeniería. Ella es una de las primeras graduadas con doctorado mujer de la Universidad de California, Berkeley, donde obtuvo su doctorado en 1984. Como ustedes saben bien, la Universidad de California, Berkeley está entre primera y segunda de las mejores escuelas de ingeniería civil del mundo y ha tenido muchos proyectos de investigación con la Fundación de Ciencia, la Fundación Nacional de Ciencia para Programas de Ingeniería de Mujeres. También obtuvo su maestría en Ingeniería Civil en la Universidad de Nuevo México y el bachillerato en la Universidad de Oklahoma. Tengo el agrado de dejarlos con la doctora Sandra Houston, una de las profesionales más destacadas en el área de la ingeniería geotécnica, específicamente en el área de la mecánica de suelos no saturados. So, with you, you can start whenever you want. Thank you very much for being here with us to this anniversary, 50th anniversary of our school. We're very pleased to have you with us.
Okay. Thank you very much for the introduction. I would like to tell everyone here that I'm quite grateful for being invited for sharing in this celebration of your 50th anniversary for the Construction Engineering Department and also the 10th anniversary for the master's degree program in highway engineering. So today I'm going to talk with you about some impediments to bringing civil engineering research into routine civil and construction engineering practice. And as I go through the presentation, I'm going to use extensively geotechnical example, and in particular, unsaturated soil mechanics, because this is the topic that I have researched for almost 4 decades now, and with which I am quite familiar with trying to implement into practice. So, some reason my presentation is hung up. There we go. So if we look at the implementation of bringing research into the practicing civil engineering's office, we find that there are many that have a role to play in whether or not the transition of the new technology takes place. So today we're going to talk about the role of educators, researchers, government and other funding agencies, and also practitioners. So everyone has a role. And I will tell you that primarily what I'm going to be talking about is the impediments. And so some of this will be, what are we doing wrong and why are we having some struggles in our implementation? So let's take a look at the example that I'm going to share with you today, which has to do with bringing unsaturated soil mechanics into civil engineering practice. And really bringing unsaturated soil mechanics into geotechnical engineering practice as well. So first, let's take a look at what is unsaturated soil mechanics. Well, unsaturated soil mechanics deals with what is going on here in the soil zone above the groundwater table. So in this region here, the soil is a little bit different than it is in the region below the groundwater table. But I will tell you that in the development of the field of geotechnical engineering, we started the process down here in the saturated zone below the groundwater table, whereas most of our infrastructure is actually developed here above the groundwater table. Now, that's not exclusive. Of course, we have some infrastructure below the groundwater table as well, but a great deal of our infrastructure, roadways, foundations for structures, slopes, many of these things. In fact, we try to keep things above the groundwater table when possible because it's simpler that way. Now, what is the difference? Well, the primary difference is that when we are above the groundwater table here in the unsaturated zone, we have negative pore water pressures, or what we call soil suction. So you're going to hear me talk about suction a lot in my example. Whereas below the groundwater table, we have positive pore water pressures, which is no surprise. We typically, under equilibrium conditions, will calculate those as the depth below the groundwater table times Y gamma W. Whereas the suction above the groundwater table is a bit more difficult to calculate. So we started, again, our geotechnical profession thinking about saturated soil, and we find that we live most of our life up here in the unsaturated zone. So what is the problem with implementation? So why is unsaturated soil mix important in geotechnical engineering practice? Well, again, a lot of things we do are above the water table. It impacts slope stability, bearing capacity, settlement, pavements, deep foundations. There's collapsible soils, which mean that they compress when they're wetted, expansive soils, which expand, dams, embankments, retaining walls. This is just a few examples of why unsaturated soils is so important in geotechnical and civil engineering. A very well-known example of why it's important is a case study of a slope in Hong Kong that was presented in 1987. So the slope that we talk about here in Hong Kong is a very high slope, 90 meters or so, relatively steep, located above the groundwater table, which is here. So we're talking about this slope above the groundwater table. And at the base of this slope is an existing building. So the idea was they were going to do some construction up here at the top of this slope and wanted to study this stability. Well, using saturated shear strength data, which is typically used in geotechnical engineering, the existing slopes were found to have a factor of safety less than 1 even before the building was to be put in place. So this was an unacceptable situation. So if we bring in unsaturated soil mechanics, now what happens is we find that above the water table here, that we actually have some negative pore water pressures or some suction. And these suctions are not great. They're in the neighborhood of 40 to 50 kPa, but they're quite stable because anytime we're above the groundwater table, we have negative pore water pressures. So look at what happens here. This red line here represents factor of safety of 1. Now, before we take into consideration soil suction, remember we were below that number, but taking into account some soil suction, you can see that the factor of safety builds and builds and builds, comes above a factor of safety of 1, and then eventually in many regions of the slope, in a very nice region here of 1.1 to 1.2, even 1.25. So the soil suction has a major impact. In addition, soil suction has a major impact on bearing capacity. Here we're looking at the ultimate bearing capacity, which is, how much stress we can put on our foundation systems, for example, versus the average suction in the profile. And as you can see, the bearing capacity increases as the suction increases, and therefore it becomes very important to take this into consideration. So if we do not consider how much additional strength or capacity we get from the soil suction in the unsaturated zone, we're over-designing all of our footings and foundation systems. So let's take a brief look here at the history of unsaturated soil mechanics. So in the 1940s and 50s, we discovered that we could actually control and measure soil suction. A lot of this work came from our friends in the soil science field, but in 1950s and or so, we were actually measuring soil suction. And unsaturated soil mechanics theory was actually developed in the 60s to the 70s, where we basically identified the role of soil suction in soil behavior. Again, 48 to 60. We started having conferences on pore pressure and suction in the 60s, and we were able to control suction and do soil test with unsaturated soils by controlling suction and also confining stress for triaxial test and for odometer test. So this was all done in the 50s and basically 50s, 60s, and up to the beginning part of the 1970s. So really 1960s to 1970s became the time when unsaturated soil mechanics really emerged as a discipline, and we had a theory behind it. And what was found in the development of the theory was that a single valued effective stress, which we learned in our first geotechnical engineering courses for saturated soils, was proposed also for unsaturated soils. So for saturated soils, most of you who've had any beginning geotechnical class know that the effective stress is the total stress minus the pore water pressure. And it was proposed that we considered an effective stress for unsaturated soils, which was the total stress minus air pressure, plus a parameter, chi, which is a function of the soil suction, multiplied by the soil suction itself, which is designated here as UA minus UW. However, in development of the theories for unsaturated soils, we found that a single valued effective stress was shown to be inadequate for describing both volume change and shear strength behavior. And in fact, the chi parameter was not degree of saturation. It was first proposed, but was limited in range, was not limited in range from 0 to 1. So it had to be something other than degree of saturation. So what was done was early on, the idea of developing an effective stress for unsaturated soils was abandoned, and we moved into a new era where unsaturated soil mechanics was really born using two independent stress state variables, which is an approach consistent with existing saturated soil mechanics methods. So when we deal with materials or soils above the groundwater table, we now have two stress state variables that we need to think about. One is the net total stress, or sigma minus UA, and the other is the soil matrix suction, or UA minus UW, sometimes shorthanded as S. So normally we will just refer to this as the soil suction, and I will do so in this presentation. So the net stress and the matrix suction were found to be effective in controlling both shear strength and volume change, but we had to keep them separate and couldn't put them into one effective stress like we did with saturated soils. So I'm still trying to change my slide, so just 1 minute. Okay, so moving on with our history of unsaturated soil mechanics, what we found was in the 1960s to 70s, we had our stress state variables of total stress and suction, and we found that there was actually no need to combine these two stresses into one equation to solve engineering problems. And in fact, we even discovered that there was no equation that was possible for a stress state description that was just one equation where we put the two stress variables together. So we just went about directly using the two separate or independent stress state variables of net total stress and matrix suction. And then in the 70s to the 90s, we moved beyond kind of the basic theory and started developing some more advanced constitutive models that were developed to describe the behavior of unsaturated soils in terms of these two stress state variables, total stress, net total stress, and suction. We had piecewise elastic models, which we started with. We developed elastoplastic models with the work of Alonso et al. In 1990, and elastoplastic hardening. So a lot of the work was done by Alonso and colleagues, and also Fredlin and Raharjo had the book that they published in 1993, which was the Unsaturated Soil Mechanics textbook. And we moved on in the 90s to the 2000s to improve methods of measuring soil suction, having had the theory under our belt. So the 90s and beyond became a period where we were looking forward to emphasizing implementation of unsaturated soil mechanics in routine geotechnical practice. And there were many discussions on this with our technical committees and conferences and so forth. So we're now in the 1990s and 2000 in particular, we're ready to implement. So how did it go? Well, the geotechnical engineering profession has had a sound theoretical basis for solving unsaturated soils problems for nearly 45 years. So let's take a look now at how we're doing on use of this theory in routine practice. And again, remember, this is an example. If you are not in geotechnical engineering, you may have your own example, but for unsaturated soils, let's take a look at what happened. First, let's take a look at the role of university professors and educators. And I say the university professor has a major role to play in implementation of new technology into practice. And why is that? It's because the university professor teaches the upcoming engineers about what they need to know as they enter the practice. But if we take a look at civil engineering classes, especially undergraduate classes, I think we need to ask the question, are we perhaps a bit stuck in the mud, or if you're in structures, stuck in the concrete, when we talk about what people need to know about civil engineering? So when we have our introductory geotechnical classes, are we teaching the same things still that we taught a long time ago? When we teach our structural engineering classes, how much have we changed? So as an example, if you look at in the introduction to geotechnical engineering classes today, what we find is that the emphasis is on laboratory tests, classification of soils, saturated or perhaps dry but not unsaturated. So saturated soil shear strength, deformation, saturated fluid flow and permeability, establishment of theories such as consolidation for deformation, which is again a saturated soil thing, flow nets saturated, Moore circle, and shear strength, usually of saturated soils. So saturated soils and single effective stress is what we're teaching today. Now, what was being taught in 1978? I happen to know because I was an undergraduate student at that time, and I took my first geotechnical course. And what was taught was laboratory tests such as classification, saturated or dry shear strength, deformation, fluid flow, permeability, saturated soils, theories such as consolidation, flow nets, Moore circle, shear strength, saturated soils, and a single valued effective stress. So if that list looks familiar to you, it's because it's exactly the same as what we're teaching today in most geotechnical introductory classes. In 45 years, I say there's been very little change in the introduction to geotechnical engineering classes. Now, once in a while, we'll toss in a few new items here or there, but I think that, some professors are actually, and including myself, I'm a little bit guilty of this. So what are some possible paths to improvement and getting out of this rut or getting out of the mud? Well, one thing we should be doing is having more conferences and open discussion on civil engineering education, development and sharing of new course materials for introductory civil engineering classes, and perhaps obtaining peer review comments on our course materials. And for example, I think it's good to see that the new Education Technical Committee for the ISSMGE in geotechnical engineering. These things are all very much needed and perhaps need more of our attention. So here was a conference that was held in 2016, which is called Shaping the Future of Geotechnical Education. It was one of the ISSMGE conferences. where it was stated by Jean-Louis Briot, professors have the unique and the most important responsibility to help young minds to think and impact their future in the most constructive way while making it fun rather than rehashing old notes. This takes energy, dedication, hard work, but the outcome is well worth the effort. We must make the effort to change the status quo of our introductory geotechnical classes. So in, I guess, a decade or maybe a little bit more back, Dr. Zapata, who will actually be speaking with you later on in this conference, and I received some funding from the National Science Foundation to develop some educational materials for introductory classes. And I'm going to share with you just a very small subset of the materials that we developed as a part of that project. And it's on the stress state of soil, starting with soil as a three-phase media, meaning I'm going to start with the soil stress state when it has the solid matrix, water, and also air. So it's the more general case. And as we go through this, you will see how we can take the three-phase media and then simplify it to the saturated soil case. So here are material types. The stress state of soil, because soil is three phases, in general, it has air and water and solid. There are actually three stresses that must be considered in describing the stress state of soil. One, the total stress, which is normally compressive in geotechnical lingo. Two, the pore air pressure, which is normally positive or zero. And the pore water pressure, which can be positive or negative, but is negative in the field where the soil is unsaturated and all three phases are present. So the pore water pressure is negative when we have solid, water, and air present. In a simplified view here, the total normal stresses, sigma, tend to push our soil particles together. And the positive pore air pressure and pore water pressures both tend to push the grains apart. So negative pore water pressure, on the other hand, tends to pull the grains together. So total stress pushes the grains together. Positive pore air pressure, positive water pressure push the grains apart. Negative pore water pressure pulls the grains together. And that's basically what you need to know about stress states. And further, it has been well demonstrated that if we choose to combine the three stresses into two net stress variables, we have two variables that we can measure and which can be applied and controlled externally to the soil, both of which tend to keep the grain particles together. The first one is what we call the net stress, or sigma minus UA, and the second is what we call the matrix suction, or just the suction, UA minus UW, which we abbreviate as S. So we can take this and simplify this for saturated soil conditions. As the soil is wetted, more of the void space is filled with water and less is with air, and in that case, the suction decreases. As the soil becomes very wet, the pore air becomes discontinuous and eventually becomes exist in just little bubbles. As the pore air becomes discontinuous and the air space in the void approaches zero, now our suction approaches zero, and UW can actually become positive when the soil is saturated. A saturated soil has only two phases, the soil matrix and water, and thus the saturated soil, there's only two stresses that are remaining, which is the total stress sigma and UW. When the pore water pressure is negative, it tends to pull the grains together. However, when the pore water pressure is positive, such as when you get significantly below the water table, the pore water pressure tends to push the grains apart. The pore water pressure is negative for saturated soils above the groundwater table, but the pore water pressure is positive for saturated soils below the groundwater table, and that's true even in the capillary zone. So if the soil is saturated and you're above the groundwater table, you're still going to have negative pore water pressures, but if you're below the water table, they're going to be positive. Now, saturated soil conditions, it's possible to combine the total stress and the pore water pressure into just one net stress because we only have two phases now. And we have one net stress that is called the effective stress in controlling the deformation response and the shear strength of saturated soils. This net stress is called the effective stress, or sigma prime, which is introduced by Terzaghi. And this is then is the familiar effective stress equation. Sigma prime effective stress is equal to sigma minus UW. So let's move on and take a look now that we've looked at educators and some of the things that I think that educators can do to help bring things into practice. Let's take a look at the role of researchers in implementation of new engineering design in routine practice. So researchers have a lot of roles to play in bringing research to practice. One is development of theory, establishment of testing methods that allow measurement and control of the relevant variables, development of constitutive models, establishment of protocols for property determination, design parameters, and design methods that can be practically used by practicing professionals, demonstration of theory and methods, and then, of course, search for continuous improvement and breakthroughs and enhanced understanding. All of these things must be done by the researchers. I would argue that we very often fall down on item 4, which is development of protocols and methods that are practically usable by professionals in routine civil engineering and geotechnical projects. So if you go to research paper conferences, often these are not student or practitioner friendly. What you'll find is researchers talking to researchers. I know this is true in my field. And a lot of times it's a very complex, and we don't boil it down to here's what you really need to know and here's the simple way to use it. So there's not a problem with this. We need this type of discussion, but we also need to carry it further. Let's take again a look at unsaturated soils conferences as an example of this. These are just a subset of some of the things that you often will see in the presentations of unsaturated soils researchers at our conferences that we have. Now, to some extent, if you're engaged in that particular discipline, then you will have no trouble following these things. But if, for example, you are new to the field, maybe you just started thinking about unsaturated soil mechanics, you may have a hard time following some of these more complex things. Another thing that I've noticed happens in research is that a lot of times we will keep revisiting the same topic over and over again, kind of like Groundhog Day, right? So we've already done that, but let's take a look because maybe we can improve on it. You know, maybe it's not quite ready. So we have a kind of hold ourselves to a high standard. So an example of this in unsaturated soil mechanics, one of the best examples I can think of is this effective stress issue. So you may recall when I went over the history of unsaturated soils that I said in the late 60s and 70s, we said, well, the single valued effective stress doesn't work for unsaturated soils. We have to use these two independent stress state variables. However, we started seeing research reemerge on whether or not there really might be an effective stress for unsaturated soils in the 2000s and beyond. And there were a lot of attempts at it in the 60s, which were all discarded because they were not proven to be not appropriate, particularly this one called the Bishop's equation here, which goes all the way back to the 50s. But in spite of this, in 2000 or so, people started looking at this again. So in spite of having a sound framework for solving unsaturated soil mechanics problems in terms of two stress state variables and having abandoned the search for a single effective stress in the 1960s, the search for a single effective stress started again around the 2000s. And here's some of the papers that started getting attention. Such, I would argue, this is just my own personal opinion, that such revisiting of settled science creates an impression with students and also with practicing engineers that maybe these new methods that we're hearing about are not yet ready for implementation. And this type of an impression can actually slow the progress in moving things into practice, in my opinion. And another thing that I find that researchers, including myself, like to do is what I call looking under the street light. This fuels incremental change. So we're going to look where we can see the easiest, as opposed to looking out here in the dark areas where we can't see anything. So let's look further into the things that we already think that we know a little bit about. This is fine, and I think there's a lot of room for this, but a lot of times this is how we get incremental change. Let's take as an example again from unsaturated soil mechanics. One of the biggest questions that remains still unanswered, we're making a little progress, but even today, is what soil suction exists under field conditions? Now, this is a very complicated question, which is largely in the dark area there, not under the street light, because look at all of the things involved. You know, we're talking about the unsaturated zone here above the groundwater table, and look at all the things going on. We have things that affect the suction in this area, include transpiration, precipitation, evaporation, evapotranspiration from plants. Oh, and then we have fluid flow, runoff, and so forth. And even the position of the groundwater table affects what's going on here. So this is a very complicated and more difficult, challenging to see. But I would say that we ought to be spending more time on this if we want our practitioners to use unsaturated soils, because they need to know what they can count on in terms of soil suction in these regions. So what soil suction can be relied on in the field conditions? This is the #1 issue related to implementation by practitioners of my field of engineering, which is unsaturated soil mechanics. But often you find that our researchers continue to refine and further refine constitutive models, adding incrementally and complication upon incremental complication, and looking under the streetlight. In some ways, looking under the streetlight or continuing to refine what we already have, this is actually easier than working towards practice-oriented protocols or working towards what we really need to advance new methods into routine practice. Because in order to implement something, you need to understand it fully so that you can then simplify it for people to use. And this is another research issue, which is related to using a different measuring stick for new engineering and science methods. So again, as an example from unsaturated soil mechanics, studies at micro level have become quite common, and these can be very illuminating in understanding unsaturated soil behavior. However, such micro-level type studies are not necessary for implementation into practice. They're needed, yes, but they don't necessarily advance us into practice. Many constitutive models today attempt to separate various types of pore water at a micro level. So, for example, attempting to quantitatively separate the two types of soil suction, which if you're in unsaturated soil mechanics, you will know that that's capillary and adsorptive water. If you're not, don't worry about it. They're at the micro level. But the micro-macro models exist for saturated soils as well. They've already been developed, and they're appropriate for special cases and also for research. However, these models do not dominate what I call the practice of geotechnical engineering. And in my opinion, they're not likely to do so for many years. So the practice is more based on macro level response, or what we call continuum mechanics. If that's okay for saturated soil mechanics, why not for unsaturated soil mechanics? Well, we can move on with our continuum macro approach and bring practitioners into the game a little bit better. So the soil stress state variables in geotechnical engineering and saturated soil mechanics have always been phenomenological, such as the effective stress. It was observed phenomenologically, that means through laboratory testing, that the effective stress that people are familiar with for saturated soils was effective in controlling shear strength and deformation of saturated soils. So a macro level approach has historically been taken in the solution to geotechnical engineering problems. And this approach has actually served us very well in coming up with many practice-based solutions to problems. And we are already ready in unsaturated soil mechanics with demonstrated macro level stresses that we know can be measured and controlled externally to the soil. And those two stress variables are the net stress, sigma minus UA, and the suction, UA minus UW or S. So we're ready at the macro level to do implementation. But sometimes using a different measuring stick, saying, oh no, we need something better. We need things at the micro level, for example, compared to what we do in saturated soil mechanics, this different measuring stick is not needed for routine application of unsaturated soils theory. In fact, a different measuring stick can slow progress towards bringing research into practice. All right, now let's turn our attention to another party, and that is the people who fund engineering research, and take a look at their role. And most of my experience, of course, is in the US. I assume it will at least have some resonance with people in Costa Rica. But the sources of research funding that I normally see are government agencies, especially in civil engineering. The reason for that is because much of our civil engineering research is dominated by public infrastructure, transportation and buildings and things for the public. But we have government agencies, private companies, and nonprofit corporations. So these are the primary sources of funding. Now, civil engineering research, as I said, is dominated by government agencies. Requests for proposals, I find, are rarely aimed at applied research or implementation of findings into practice. Rather, a lot of times they're focused more on fundamental things as opposed to applied research. Now, applied research is really what we need to implement our more fundamentally based research into the practice of civil engineering. So let's look at the role of agencies and other funding agencies a little further here. If we look at the funding source in the United States, for example, in civil engineering, one of our major sources is the National Science Foundation. It is primarily for fundamental research, that which has the potential to transform and which addresses greater issues of society as climate change and renewable energy. Well, of course, we need those things. You know, this is very important. We all want to see research and advancement on the front of climate change and energy. So, for example, but the funding for applied research is actually very limited in civil engineering in the United States. So it's difficult to bring new things into routine. What are we foundation design, for example? Now, one possible direction for improvement here might be to further emphasize what we call performance-based methodology. This is where infrastructure owners emphasize their characteristics of the final system, the structure, components, material, products, services, or activity, rather than the processes or other inputs required to produce it. Now, what does that mean? Well, performance-based methodology is going to bring to the forefront innovation, adoption of new technology, and very importantly for implementation into practice, life cycle performance. We need funding agencies, including industry and owners of civil infrastructure, to focus on a higher percentage of their funds on applied research that is directly linked to performance and life cycle cost of infrastructure that, frankly, is still being developed today and certainly improved today. So we're working on it constantly, and we need these new ideas implemented. All right, now finally, we'll talk about the role of practitioners. Now, practitioners probably may have a little less of a role. However, they do have some, of course, responsibility in implementation. They do face possible constraints or pressures working against implementation of new methods, that's for sure. Often there's a low bid focus on contract awards. So whoever has the lowest bid gets the contract, and that does not really facilitate innovation in most cases. Or in civil engineering design, we are still very heavily focused on codes, you know, regulations, codes, building, you know, universal building code and so forth. Another factor, and this is a big factor in the United States, is fear of litigation or liability if something goes wrong. This always comes back on the practitioner, not on the researcher or the student or the funding agency. It's the practitioner that gets this. They're also faced with time constraints for continuing education. And in civil engineering, there's quite a heavy emphasis on on-the-job training. So these are things that tend to slow us a bit in our implementation efforts. Again, let's take a look at unsaturated soil mechanics as an example. If we look at the practice of geotechnical engineering, I mentioned early on in the presentation that a lot of our infrastructure is actually developed in the region above the groundwater table. So for this reason, geotechnical engineers have always had to deal with unsaturated soils. It's just that they've been doing it in the absence of our unsaturated soils theories. So could they do better with sound unsaturated soil theory? Well, yes, because here's what's happening today. There are basically two approaches that practicing engineers are using in dealing with unsaturated soils, which they do daily. They use either unconservative designs and procedures that lead to failures or construction difficulties. Now, why is that? That's because they might assume that the soil will never get wet or saturated. In other words, it's going to stay in the same dry state that it exists today. Now, we happen to know that when a soil gets wet, that the suction goes down and therefore the bearing capacity decreases, the factor of safety against slope stability decreases. So if you assume it never gets wet, that's going to be unconservative. However, most of the time, the practicing engineer is going to be over conservative. That leads to that. Now, what's wrong with being over conservative? Meaning, let's assume it gets wet all the time. It's always wet. It's always saturated. If we assume that about the soil, this leads to much higher than necessary construction cost. Why? Because we have built-in factor of safety that are much, much larger than we really even understand. So assuming a soil will always get fully wetted is over conservative, and we're throwing away a lot of money, a lot of which is money that is basically coming from the public or our governments. So this is not, this is really not sound engineering practice, and it would be better to move beyond this. So implementation, again, using unsaturated soil mechanics as an example, the most important thing that we need to recognize is the role of the controlling stress variables, net stress and suction. And be willing to adopt simpler models rather than ignoring unsaturated soil theory. Be willing to be conservative with respect to how much suction can be relied on in the field, but not overly conservative so that we're having very, very high factors of safety and throwing away too much money. So implementation of unsaturated soils theory in routine geotechnical practice is a critical part of the minimization of the cost of maintenance, repair, and building of our infrastructure, and therefore a critical part of life cycle cost. So I've had the chance to ask many practitioners over the decades that I've been studying in this field as to why they don't use unsaturated soil mechanics. And so when I ask practitioners why they don't use unsaturated soil mechanics theory, the answers generally have nothing to do with the debate that we find ourselves having in research about the two stress state variable versus effective stress. In fact, most practitioners are completely convinced that soil suction has an effect on the response of unsaturated soils. That's been demonstrated to them. The problem, rather, is that most geotechnical engineers are not sure what they can rely on for soil suction under field conditions. So that was the big question, remember, that doesn't lie under the streetlight. The primary reason that practitioners give to me about why they're not using unsaturated soil mechanics is litigation concern. When they use something new, it's not just in geotechnical engineering, but in any field. When they use something new, they have a worry that they might be liable if something goes wrong, or that there will be legal suits brought against them. And this is particularly true when practice protocols have not been laid out by researchers in well-established, peer-reviewed literature, because the practitioners rely on the researchers to basically give them the applied studies that they need in order to implement without so much litigation concern. So I guess we've come full circle now back to researchers, not quite to educators yet. But let's ask ourselves, if you don't believe me, is the fear of litigation really driving our routine civil engineering practice? And I say the answer is to a large extent, not exclusively, but it certainly plays a role. Here's a quote from Dusenberry at the meeting of ASCE's grand challenge to reduce infrastructure lifecycle cost by 50% by 2025. So ASCE had a challenge to reduce infrastructure lifecycle cost by 50% by 2025. Wonder how we're doing. Well, anyway, here's what Dusenberry says. You know, I really think that we've done this to ourselves. The legal system hasn't done this to us. Movement towards prescriptive codes long precedes our current litigious bent. I think our profession is naturally conservative because of our concern for life safety. So we actually become very conservative, and I think we've stepped away from responsibilities that civil engineers used to have. We're creating our own mess. Now, I would say that a responsibility of civil engineers is to actually think about the life cycle cost and how much money we're spending. And this money can come in terms of just dollars or environmental harm, climate degradation, and so forth. So this is our job, but we're very conservative. We don't want to do something new. So in a way, a practitioner kind of views themselves of swimming around with a bunch of other practitioners out in the ocean with the lawyer right here in the middle. Perhaps an exaggeration, but certainly some truth to it. So you might ask yourself, if I talk to practicing engineers about why is it that you should take the leap and go ahead and tie some of this new engineering science and design and routine practice? Why should you do it? Well, it leads to better and more cost-effective civil engineering solutions. Very conservative and safe old methods are also not always the best. And as we enter into a period of rapid infrastructure growth, much of which is routine, we need cost-effective methods in terms of money, climate, and other environmental considerations. So it's best to go ahead and take the leap and do these life cycle cost analyses so that we're doing better engineering. So the practitioner does have some responsibility to move forward here too. Now, I've been a little bit negative here talking about why we don't implement research into practice, but it's certainly true that there are many, many exciting projects going on in civil engineering and many new approaches. And I don't want to downplay that because I think that we are doing a lot of innovation in civil engineering. Just a few examples that I just borrowed from McFadden 23. The Venetian tidal barrier. It could be used for future flood protection. It's unique in its design of using the mobile gates that can be raised to protect Venice from floodwaters. And in fact, this type of technology could actually be used to control floods in many other areas. Or another example, the Alvarado water treatment plant, designed to last 75 years and to double the current filtration capacity of San Diego, which is a shocking 800,000 meters cubed a day. And it will be partially solar powered. So there's some innovation here in water treatment. Or the Jeddah Tower, the Saudi Arabia, is a skyscraper of the future. When completed, it will be the tallest skyscraper in the world, standing 1 kilometer tall. It will also be sustainable, built under the auspices of the architectural philosophy of global environmental contextualism. So these are just 3 examples. There's many, many of these, but these are largely focused on very visible, high dollar projects and not the routine civil engineering design. I'm going to give you another example from my unsaturated soil mechanics. So This happens to be a very innovative retaining wall design and slope stabilization, which makes heavy use of unsaturated soil theory. So this is actually the retaining wall system. As you can see, it's very aesthetically pleasing with plants and so forth. So remember, I told you that the soil suction depends on so many things, including infiltration, rainfall, evaporation, evapotranspiration from plants. So what is being done here is that there is a barrier system here that is made out of unsaturated soils and plants and various different media here, designed so as to control the suction that is actually can be counted on back here in the compacted soil. And it allows you to build steeper walls, stabilize slopes, and so forth. So very innovative and exciting stuff that actually is happening today. However, I would argue that we need to take some of these more exciting things that are happening and innovations and bringing new theory into practice. And it's time to bring research and innovation to our daily routine civil and construction engineering. And we've talked about today some of the things that are impediments to moving research into practice. Something just for you to think about as you go through your role as an educator, a researcher, maybe a funder of grants, and maybe even as a practitioner. Educators certainly need to look at, what are we teaching? Is it stayed? Is it old and stayed, or is it new? And is it bringing new material in the faith to the students that are go out into the workforce? Are we presenting our work in such a complicated fashion as researchers that we're not giving that applied emphasis to people so that they can use it? Or, are we missing a step in what researchers should be doing? Should we be looking at how we're funding projects and putting more emphasis onto applied research? I would say yes. And as practitioners, are we overly worried about liability and litigation? And, so those are some things, take homes for you to think about. And with that, I will thank you for your attention today and see if there are any questions.
Thank you, Dr. Houston, very much for your excellent presentation. Very nice. So we're going to move to questions. Por favor, si tienen algunas preguntas, la forma que hemos decidido hacerlo es con el micrófono. Pueden levantar su mano y hacer su pregunta. Pueden hacerla en inglés o pueden hacerla en español. Alonso Poveda Montoya.
Gracias, buenas noches. Gracias, profesora Sandra Houston, por la presentación. La primera pregunta que le quería realizar es, bueno, si puede repetir un poco sobre el estado del arte de los suelos no saturados y hacia dónde es que se debe dirigir las investigaciones relacionadas a este tema.
A ver si puedo traducir. Thank you very much for your presentation. And he wants you to, if you can explain a little bit more about the unsaturated soil mechanics state of the art, and where do you think research should move on to?
Yes, I can. This particular presentation was not very focused on the state of the art, but rather on how do we move forward into practice. So it was much more practice-based. But as what I see happening in unsaturated soil mechanics is that we're playing a heavy role in things that are related to climate change, because there's the soil, the surface of the earth atmosphere interaction is a very major part of our climate change studies. And I think that we have a major role to play there, and many of us are. We also have major roles to play in the energy and things such as, thermal energy sources, subsurface energy sources, foundation systems for windmills and various things of that nature. Looking at the for radioactive waste disposal, looking at the thermomechanical aspects of unsaturated soil mechanics. So these are sort of some of the new directions that we're seeing. And we are beginning to see more interaction, for example, in fields like waste management and control of pollutants into our environment and those kinds of things. So that's, I think, a direction that we're taking. Meanwhile, however, I think we need to, as a profession, resolve how we're going to model our soils and our constituent models that we're going to advance forward for people to use. And so I think that we are still spending quite a bit of time on that, as opposed to perhaps looking at how we can implement these things into not just the practice, the daily practice of geotechnical engineering, but also implementing these theories into other subsets of geotechnical engineering, geoenvironmental engineering, energy geotechniques, biogeoengineering, and so forth. So we need to be able to communicate better so that we can have more impact where we rightly should be. Things like, when we have fires and it changes the soil. These are very important topics that we need to be involved in. That I think that if we could communicate more clearly, we could we could make more impact. So.
Yeah, thank you very much, Professor. Tengo otra pregunta. Tal vez la puedo hacer de una vez.
Está bien. He has another question.
Yeah.
Sería a nivel, si considera que actualmente a nivel de laboratorio tenemos los equipos necesarios para continuar con las investigaciones relacionadas a suelos no saturados, o si también se requiere innovar en este campo.
Okay, this question is focused on lab equipment. If you think that to continue on saturated soil research, we need new equipment, innovate on new equipment, or we have what we need.
Yeah, I would say that with regard to lab equipment, that we have what we need to move forward, but there is always room for innovation. Okay, and there's always opportunity there. So, but we can definitely, we've shown that we can definitely measure soil suction. Sometimes directly up to certain levels, but we can even indirectly obtain soil suction values. We can control our net total stress in the laboratory. We can make measurements that are indicative and pretty good measurements of soil suction even in the field, particularly when we have low suction values. But even at high suction values, we've got reasonably good methods to obtain suction values. So my position is this: provided we can measure and control and predict the stress state variables of interest, that is, the stress state variables controlling the performance of the soil as an engineering material, then we are in pretty good shape. So some of the things I'm aware of, maybe you're in unsaturated soil mechanics, I don't know, but certainly some of the work the meter group has done in bringing in, for example, the WP4C, which gives us the capability of getting higher suctions than we have by relating to relative humidity. That's something very important. We can do osmotic control of suction. We can do still the axis translation, which is, in my opinion, valid and appropriate. And then we have many researchers who've done correlations with between water content of you know, various different, you know, ceramic type materials and using those, for example, to get field suction measurements, or even between water content and suction and calibrating methods and so forth. So, is there more room? Absolutely. I think in particular, when it comes to volume change measurement during laboratory testing, we could do way better. Understanding things like, you know, when we do triaxial test, how is our radial strains distributed, you know, across the specimen and so on. So yes, room for improvement, but are we in pretty good shape? I say that we're certainly ready to implement. Yes.
Thank you, Professor.
¿Alguien más con alguna pregunta? David Murillo.
Yes. Thank you for the presentation. I hope that I can make myself be understood with this question. Could it be that the application of unsaturated soil research applied on environmentally friendly construction practices will lead to more attention into applying this research on the field? So tie it a little to eco-friendly practices so that it leaves the realm of theory.
Yeah, I certainly think that the focus on environmental concerns is brings more attention to the unsaturated soil mechanics field. I mean, even when you look at just things like dust control, I mean, you know what's happening there again at the soil atmosphere surface is very important to this, or and definitely in the pollutant migration, because we first pass through the vadose zone before we move to the drinking water source. But even in the construction processes itself, I believe that there will be opportunity. Some of that actually is sort of a financial aspect of it. You know, I mean, if we can reduce the amount of concrete that needs to be used, for example, we can have an impact on the greenhouse gases and so forth that are generated. And how do we do that? Well, if we can rely on some of the soil suction, then we don't have to be quite so over conservative. We don't have to use quite so much concrete. And, you know, so yeah, there's a lot of, I think, places where environmental emphasis can bring more attention on the unsaturated soil mechanics field. If I believe that was your question. This hopefully,
yes. Yeah, thanks for the answer.
Gracias. ¿Alguna otra pregunta? Emilio Arroyo.
Yeah, well, first of all, thank you for the presentation. And you said that unsaturated soil mechanics theory or classes haven't changed that much in the last 30 or 40 years. Do you think this is bound to change in the following years or ever?
I think we have to change. Again, I'm taking a very broad brush here in describing what people are doing, right? So I always think of one of my colleagues who would, you know, bring out his old yellowed papers and, you know, present his introductory class. Well, we still need the fundamentals. We still have to teach a lot of the same things. So I'm not being critical of that, but I think that we could certainly improve on the manner in which we introduce students, certainly to geotechnical engineering. Yes. So and it's true in other civil engineering as well, I believe, from conversations with my colleagues. We are staid. We are a conservative profession. We don't like change, but we must. And I think that you know, just like we must recognize that climate change is real. You know, we got to recognize that it's time to step up as a profession, because we have, as civil engineers, a heavy influence on the performance of our Earth system. quite a heavy influence, in fact. So I hope we try. I think we need to talk more about education than we do. We tend to just kind of get through the teaching process perhaps sometimes and then emphasize more our research. But there's opportunities in education as well. And I think that we would be well served as a profession if we could advance a bit. That's my thought.
Thank you.
Andres Pino has a question. No se escucha, Andrés. Tiene el micrófono muteado. Ok. Tal vez si la hace ahí en el chat la pregunta. ¿Quiere escribirla o? Asking him to write it on the chat. I guess I can ask a question.
It's okay.
Oh, no. Andrés. ¿Quién habló? Well, I'm going to ask my question.
Sure.
My question is on the teaching side. It's kind of related to what Emilio just asked. And it's a two-part question. First, sometimes professor, in order to improve the courses, we probably need to talk more about it, like you just said. But sometimes professors don't want to. Sometimes egos, right? You don't really want other people to see what you're doing. What do you think is a good way to deal with that, right? To start that conversation or improve that conversation of what we're teaching and how we can do it better. And second part of the question is, now that we need to consider climate change mitigation in our courses, do you know of any course, undergrad or graduate level course that addresses the climate change mitigation and unsaturated soil mechanics anywhere in the US or anywhere in the world? If you know of anybody, any program that is actually doing that right now.
I'll answer your second question first because it's easier. And that is that I don't know of anyone who has a course or lecture material specifically aimed at climate change. However, I do know that many people are pursuing this topic in their research proposals and in conferences and things of that. So I think we're at the early stages of that. And there's probably some discussions in graduate level courses surrounding the interplay between climate change and unsaturated soil mechanics, but it's, as far as I know, it's not a primary topic in any of the currently offered courses. But hopefully that will change. Now back to your part one question, which is, I believe that part of the problem is, like you say, no one likes a peer review. No one likes to have someone sitting in the audience as they're talking to their students, right? In fact, today, I told my husband, I said, I don't want you in here while I'm talking because, it just bothers me, right? So I get it. No one likes to have someone who might be judging them as they're presenting. But part of the problem is that I think we're not willing to be honest about our teaching with our colleagues, which is most of us are not fully comfortable with how we're teaching and what we're presenting. And we really do need to open up the dialogue and just be more sincere and honest about it. Peer reviews are normally not well received. I can fall back on my experience as department chair to tell you that. I think we need it, but it's very uncomfortable. People worry that it's going to somehow impact their their career, their job, their standing in the department. So I believe maybe we need more informal type discussions, we need an environment where people feel comfortable saying, yeah, I'm still teaching this, and I feel like maybe I could do something better. What do you do? Or do you have any ideas and that kind of thing? It needs to be more informal. So it's a very difficult, very, very difficult, which is why I think that my criticism of what we're doing in education is probably, more valid than most of us would like to admit. I mean, when I talk to some of my colleagues, they would say, oh no, I'm doing new stuff. I'm bringing new stuff into the picture. But when you look at how we test our students, you can see that what we're testing them on, what we're challenging them to answer questions on when we judge them as whether or not they're ready to practice civil engineering is on the older methodologies, right? So in a certain sense, when I corner people, they'll say, yes, I'm actually kind of teaching to the test, right? Just like that we criticize our high school teachers of doing sometimes, right? So it's tough, but basically we have to just, begin to be a little more honest. And it's a challenge.
Yeah.
Not an
Thank
answer.
you.
Not an answer.
Well, I have two questions in the chat I'm going to read. Let's see. I wanted to ask, how can we as students do our part on changing how things are being taught nowadays? Thank you for your amazing presentation. That's the first one.
Okay. Thank you for your question. Yeah, a lot of times I think that students don't get many opportunities to really participate in what's being taught in class. And I myself would say that, university professors, we all think that we know better than you do what needs to be taught. But I find that what motivates me as a professor to bring new material into my classroom is when students really express interest in my field, when they express an interest in taking it beyond what's just been taught in class, and enthusiasm. So there's always an opportunity for students, or typically there's an opportunity for students at the end of the class to say, well, I didn't like this, this, and this. Okay, that's a negative approach, which oftentimes doesn't work. But I think that students can be just more engaged, more enthusiastic, or saying, things like, oh, I was reading about this particular project, and it seems to me that it has something to do with geotechnical engineering. What can you, what can you tell me about your field that's addressing this new and important project? Those kinds of things. But enthusiasm, to me, always very important to motivate me to do something different. So yeah, I like to teach people who like to learn.
Esa pregunta fue Andrés, ¿verdad? Entonces, espero que eso sea lo que quería preguntar. Now I have another question from Mauricio Araya, who has some problems with the internet, so he wrote it on the chat.
Yes.
What do you think about using emulators or virtual laboratories to complement the teaching of soil mechanics or other subjects?
We're probably going to go in that direction, whether we think we should or should not. And so I would take a positive attitude towards it. I haven't seen any yet that I think are particularly exciting or effective, but I think we could develop virtual laboratories or emulators, and some of those might, I know in centrifuge work they've worked somewhat in this direction, but in other fields I've seen things done quite well as far as virtual laboratories. So my daughter actually took her high school online and she took a biology class, and they had some virtual experiments in this class, which I watched. And they actually gave the student the opportunity to make decisions, for example, on what they were going to add to their petri dish, and they gave them time lapses on what if they did this or if they did that, and it was pretty effective in my opinion. So I think there's opportunities there. Geotechnical engineering, because things don't move too much, it's a little bit more challenging, but I still think we could probably do it. So I'm hopeful that I think we're going to have to move that way a little bit.
Yeah. Thank you so much. ¿Alguna otra pregunta? No sé si estamos o si alguien tiene algo que no se quede ahí con las ganas. Okay, I guess we have no more questions.
Okay.
So I want to thank you, Dr. Houston, for your presentation. It was very exciting, very nice. And thank you for being here. So you were always willing to participate on our anniversary and take a part of your time or your effort preparing the presentation. We're really happy that you were here with us. Thank you very much.
Well, thank you very much for your time and attention today. I appreciate it. And I'm glad to be able to participate in your anniversary celebration event here. So I hope the rest of it goes very well for you.
Thank you.
Yeah.
Bueno, entonces muchas gracias por estar acá con nosotros. Esta fue la presentación de la doctora Houston y tendremos unas cuantas presentaciones más en nuestra área, internacionales también, y las próximas son en español. Para que tomen eso en cuenta. Y muchas gracias por participar y por asistir. Buenas noches.